for loop.
Thank you very much, Pablo. Thank you very much for the invitation. It would have been nice to have been in Argentina. So in a way, the title of my talk looks quite cryptic. And I think this is maybe the first time in my life where I will not clearly explain everything that's on the title. And this is because, in a way, to fit the topic of this seminar, I decided that I'm going to divide things in two. So the first thing I will do is I will talk about the Gaussian prefill, which I'm happy that it was already introduced at least quickly. And what I want to do in the first part is to tell you that the Gaussian prefill itself is just a branching random walk, and to explain quite quickly, because of the time, how one gets this construction, at least intuitively. And then I already told you this, the Gaussian prefill is going to be just a branching random walk, but in a way of, it has a weird branching structure. And this CLE4 that's in the title will represent the geometry of this branching structure. And I will tell you one of the results we have about how big or how exactly it works, this branching structure. So it will be, so I hope it will be quite, so I don't know if I hope, but it will be quite informal, in the sense that I will not get exactly in every proof, and I will just try to give an overview of what I'm saying. So the Gaussian prefill is just on a graph, which in our case will be a subset of C2, will just be a Gaussian, so it will just be a function. So it's a random function that takes value 0 in the boundary of the set of the graph, and in the rest of the point, the probability distribution is going to be given by a Gibbs measure with energy given by the Dirichlet energy. So it's just this object. So this feels quite it feels quite cryptic, but there is another way to think about it. Is just, well, it is a Gaussian process whose covariance is given by the Green's function. And here, as Marek did before, I'm going to use the Green's function of the graph, but in fact, it is not important. It's just important for the constant. So here is a profile image of a discrete Gaussian prefill in a 30 by 30 grid. And as it was discussed before, the Gaussian prefill, we know a lot about the maximum of the Gaussian prefill, and I'm really sorry to not mention everyone. So this result, I took it from Branson and Saituni, where it says that the maximum behaves like 2 times a certain constant sigma n. So when n is one has to think as the log of the size, minus 3/4, and you have the log n. So if, as we have already put attention in the morning, this feels like a branching random walk. And what is the branching random walk? It's the following. You start in a square. You choose a Gaussian random variable, let's say x1, which is normal with mean 0 and variance sigma square. So the sigma we defined before. And then let's say you divide this in 4. And then to each one of these squares, you add another IID random normal random variable with the same variance. Yes. So you are just like a branching random walk, but the correlation between these 4 is just in the x1 term. All the other ones are independent. And of course, you divide in 4 and 6, and when you see the maximum, it will be of the same order. So the question is this? So is this a real thing? So it feels like branching random walk and the Gaussian prefill in a certain way belong to a same universality class, but can one actually couple them in a certain reasonable way, or can one see the Gaussian prefill as a branching random walk? So the answer is going to be positive, and the first part of the talk would be just to try to explain to you what is this result. And in fact, for this to be equal, for this to be exactly the case, we need to go not to the discrete case, but we will need to go to the continuous. So okay, maybe first, why talk about the Gaussian free field apart from this branching random walk story? Why to talk about the Gaussian free field when one is talking in a random walk setting? Is because the Gaussian free field is in a way a random walk, yes, but where the time set, so a random walk, let's say it's x, is a function that goes from the natural numbers to the real numbers, and one wants to say, okay, but I don't believe that time is one-dimensional. Let's put it two-dimensional. So it will be in the discrete case, it was a lambda contained in C2, for example. And this is my Gaussian free field. And in a way, it is the natural generalization of a random walk when time is a two-dimensional object. And in this case, one wants to build the same thing on the continuum. So on the continuum, it's going to be the generalization of Brownian motion. So if you have Brownian motion as a function that goes from the positive numbers to R, the Gaussian free field will go from a domain to R. Okay, and as we do it in the discrete, well, it's just going to be the central Gaussian process, yes, with covariance. I will take the green. It's the central Gaussian process with covariance given by the green function. And up to now, everything looks easy. It's easy to define, and until one realized that there is a big problem here, is that the green function on the diagonal explodes. So on the discrete, this was correctly, it is exploding, but it's bounded on n, but not on the continuum. So then the first intuition one could have is that, okay, maybe there is not such an object on the continuum. It works well on the discrete, but there is no way to make sense of it on the continuum. And well, this could be a possibility, but maybe the second, after one thinks a lot about it, one can say, okay, maybe this is not well defined. So one cannot define the Gaussian free field at a given point, but maybe one can define the average of the Gaussian free field against a smooth function f. So one think of it as a Schwarz distribution or as a generalized. And in fact, this is the case. One can construct the Gaussian free field like this, and one can say, so this for me is equal to the integral of phi x against fx. So one can say, okay, I'm going to define my Gaussian free field as a Gaussian process indexed by the smooth function. So it's indexed by the smooth function, and it will be a central Gaussian process with covariance given by the green function in this sense. And now we take another profile picture, but this time, as you can see, you have something which is pretty rough. And this, and in fact, one can prove that there is no random function in L2 that can represent this object. However, for people to stay, let's say, more comfortable, it lives in a decent sovereign space. Let's put H minus epsilon. So for those who don't know it, it's just a distribution, but things are not okay. And of course, we have convergence of the discrete case to the continuum one. And in fact, it's quite nice. It is a convergence without normalization. So it is not as in the case of the random walk when one divides by 1 over square root n. And here there is no such a division. And in what sense it's converging? It's converging in the sense that the approximated integral. So if I have a domain, so I have a domain D, and I approximate it better and better by a grid, then the approximated integral of my field is converging to the integral of the Gaussian free field against this function. And so then we give you some basic properties of the continuum Gaussian free field, and which will give you certain intuition that things are weird. And the main one is the conformal invariance. So in dimension 2, the green, and this is the only dimension where this happens, the green function is conformally invariant. So if I have a domain here that is conformally mapped, let's say, to a circle, I can read the green function here by just a push forward of the green function on the circle. And what does this mean for the Gaussian free field? The Gaussian free field it means that the Gaussian free field is conformally invariant in law in a way. So if one could define the pointwise value of the Gaussian free field, the law of the value of a Gaussian free field in a domain D at a given point is equal to the law of the Gaussian free field of the value of the Gaussian free field in a given point, let's say, for the domain D prime. And this in a way explains why we do not need to rescale the Gaussian free field from the discrete to the continuum. So this no rescaling comes from this self-similar object. And in a way, what will be useful to you is that in a big square, we are seeing exactly the same that in a smaller square. Okay, so up to now I have told you about the Gaussian free field on the continuum, and I told you that the Gaussian free field is going to have it's going to be the generalization of Brownian motion. And what we are going to do is now I want to introduce a weak Markov property that will give us the first intuition on why the Gaussian free field looks like a branching random walk. A branch. Okay. So is it better? Okay, maybe I'm going to do that. So let's take a domain like this. So usually I would explain this in more detail, but the idea is the following. So imagine you have a Gaussian free field on a domain. In a way, you know that it's zero on the boundary, and you want to know what are the values of this Gaussian free field conditioned on this set A. So you know what's going on A. So the set A may be disconnected like this one, so this A, and then you want to know what's going on with the law. So then, because these things are Gaussian, the answer is quite nice, and the answer is the following: the Gaussian free field can be written as a sum of two objects. One is the expected value of the field given what I am seeing on A. Yes, and the other one is the fluctuation away from the conditional mean. Yes. So what happens is that they are both, thanks to the Gaussianity, in fact, they are independent. The conditional law of the Gaussian free field given A is harmonic outside A. And this is quite nice because harmonic distributions, harmonic generalized functions are harmonic functions. So in fact, there is a function that it in a certain way represents the harmonic extensions of the values the Gaussian free field on this boundary. And the fluctuation away from this mean has, like the Brownian motion, it has the same law as the original one, but in a smaller domain. So it's a Gaussian free field, but outside here in the red, so in this part. Okay, so this gives us the first intuition on why the Gaussian free field is or it belongs to the universality class of the branching random walk. It's because, okay, I start with the Gaussian free field and I'm going to discover it in a way that feels like I'm discovering a branching random walk. So I'm going to first use the Markov property on these two lines. So I will learn what is the value of the Gaussian free field in these two gray lines. And what I will obtain a harmonic function here by A. So there is a function here that I do not control, and it's highly correlated between one side and the other, plus one term, which are Gaussian free fields that they are independent, because these things separate in four. In fact, the greens are independent in each one. So I'm going to call this phi I1, phi 2, phi 3, and phi 4. Okay, I put it down. Okay. So as you can see, there are four independent Gaussian free fields. So I have this harmonic function plus something that behaves independently in both sides, and then I will redivide it. And what happens is that I will obtain, of course, I will obtain the same phi A in this part, which is correlated everywhere. Okay, you get the idea. But then I will get here, I will get a phi B, which only depends on the green part. So here, this is the same. This is phi B1, put it that way. But here I will obtain phi B2. This is completely independent from the ones on top. And then, so this, and then I have something which is independent in each one of them. So I have this phi B. So this phi b is IID in each one of the on this square. So one feels already, and this idea, of course, it works on the discrete also, and this is how the first works on relating the branching random walk with the Gaussian free field stuff. However, this is not exactly a branching random walk. So if one wants to work with this, it is hard. One has to think about it. One has to think about what these harmonic functions are doing, and that they are not homogeneous. They are not homogeneous everywhere on the square, so one has to be careful. So if we want to have this exact branching random walk I promised, then one needs to work with one does not need to divide with this not clearly, let's say these are not the most intelligent lines one can choose, because maybe there is something else I can choose so we can get exactly a branching random walk. And for that, one needs a stronger Markov property, which is the strong Markov property. One needs to somehow separate my domain by a random set. So to generalize the weak Markov property, we define a strong Markov property, and we need what we will call stopping sets or local sets. And what's a stopping set? It's a random set, such that if I define a given set, a given closed set C, the event that A is contained in C, so it is the same, if you think about it, the same as stopping times. Stopping times is T smaller than tau, tau smaller than T, belongs to Ft. And here we replace the subset, the smaller or equal by a subset, and it's exactly the same definition. So the event that A is contained in C belongs to the information I'm seeing in C. And if one has this, one has a strong Markov property, meaning that if that they have the same properties as before, but now not for a deterministic set, but for a local set. And the main difference is that now phi A is not independent of phi super A. There is, if I know one, I know the domain of the other, so they are correlated, but the only correlation is given by the geometric information given by A. Yeah? So if I condition on the geometry of A, I know exactly that they are exactly independent. We have the harmonicity of the conditional expectation, and we have the Gaussian free field path of the fluctuation. So let me give you a quick example of a local set so we can fix ideas. Imagine that I have this annuli, so my set is the green path, and this inner radius is 2 to the minus n, and let's say that the outer radius is 1. And what I say here is the following. So each one of them, I have countably many of these sets. So for each one of them, I do have a weak Markov property. And what one can do is say, okay, for each one of them, then I have a harmonic function that takes real values here at 0. Let's say phi an at 0, and I will choose. I will start from n equal 1, n equal 2, and I will stop at the moment that this harmonic function at the value 0 takes overcomes the value 1. And this is quite nice, and I can compute things. And it will give me a random set that, in fact, it's quite clear if one knows probability that it will produce a Markov decomposition. But what we will need is a better set. So if we want to go to this branching random walk world, we need a better set than this one. We need a set that is actually looking at the values not only at 0 of the harmonic function, but in a way everywhere. And what is a good object to look at? It is the following one. So it will be an intuition saying, okay, we want to define a local set of the field that it's the following. We say that a point, okay, a point belongs to this set, so it's a random set, if there is a path going to the boundary in which the Gaussian free field takes value between minus a and b. And this feels natural. However, there is a big problem. So if we were in the continuum, on the discrete, we could define this set and it will be clearly local. But the problem is that on the continuum, we are not able to define the values of the Gaussian free field at a given point. This is not possible. So maybe, of course, so this is not well defined. So as you have seen in the continuum with the Gaussian free field, one needs to be careful. One needs to have a good, one needs to always take alternative definitions because the classical things will not work. And the way we define it is an axiomatic way. And by that I mean, okay, imagine that the set we will call A minus AB exists. Well, if it exists, I can explore it from the boundary in a way that it's Markovian. So I can go from the boundary, and each time I see a value, I continue or stop. So it has to be a local set. And furthermore, if my set is here, for example, and I get outside the set, I stop, I did not get in because either I saw the value minus A or I saw the value B. So what I want to say is that this the harmonic path given because it's a local set, well, it's only a harmonic, so it's a function. So I said there is no mass on the set itself. So it's a function. And phi A minus AB only takes values on minus A or B. So there are just two possible values. And what happens, and what's proven by Aru, Werner, and myself, and by Lupu and myself, this is in the case of simply connected domains. This is multiply connected. We will need both. Is that if A and B are sufficiently separated enough, so then there exists a unique such local set by the ones we defined before. And in fact, it doesn't exist if I'm not sufficiently separated. And this sufficiently separation, we do have exact value, is 2 lambda. And this lambda corresponds, I put lambda because it corresponds to a normalization of the field. But in this case, it comes back to this number. We will not need to remember it. So let me give you one example. So you have A minus lambda lambda. So you have this fractal set that we know a lot of things about. The one I want to concentrate is this A minus 2 lambda 2 lambda. And in fact, this was the first of such a set that was found before the biggest theorem, the general theorem, and it is in fact maybe the most interesting. So this A minus 2 lambda 2 lambda, it has the following property, and it's the only one. So we proved this with Juhan Aru. It's the only one that has this property. It is, imagine that someone just gives you this set, yes? So someone gives you this set, which is the black path, and asks you, what can you say about the law of the values? No, you know that given the black path, I can have either inside there is a harmonic function that takes value either minus 2 lambda or 2 lambda, as you can see here. This is and then what happens is that if you condition on the geometry, you know nothing about what are the values of the labels, and furthermore the values are IID. So in fact, we obtain an IID. We obtain so if we can sample this black path, and we want to recover the Gaussian free field, what we need to do is to toss a coin in each one of on the y path, and then assign to each one the sign of minus 2 lambda and 2 lambda, and then sample a Gaussian free field inside. Or a better way. So if we do this in the first step, then what we know that what we have inside of this step, what there is inside of this one, is a Gaussian free field. So we can redo this. So we can sample this A minus 2 lambda 2 lambda. We get either minus 2 lambda and 2 lambda, and then we can sample again in this domain. And what we will obtain is another local set, but we'll have boundary values 0 or minus 4 lambda. So this is the way we build exactly a Gaussian free field out of a branching random walk. If one takes this, if one iterates this infinitely many times, one in fact obtains a Gaussian free field. So the Gaussian free field is in fact a branching random walk, but where the branching structure is first of all is infinite. So each time I am branching in infinitely many childs, and furthermore, in each of these, yes, okay, and each one has different weights and positions. So furthermore, Miller and Cecil proved that the law of this set is a CLE4. Well, they announced the result, we prove it afterwards, but it is a CLE4 which can be built also using a Brownian loop soup, which is quite interesting, and sadly I will not get onto it. So at least I introduced the CLE4. It is this object. And we know a lot about it. We know its dimension. We know it's conformal invariant because the Gaussian free field is conformally invariant. Out of this construction, we cannot only construct. We are not only able to construct the Gaussian free field, but in fact, as a parallel with Brown's random walk, where you have this exponential martingales and this derivative martingale, in fact, we can do the same case here, and they correspond the limits to what is called a Levin quantum gravity, and with the critical Levin quantum gravity, there's quite nice stories over there. And what I want to do in my last 5 minutes is at least tell you a really surprising result, which tells you about how big is the loop surrounding zero. So let me give you an idea. So you have this CLE4, and the question here, so it is the third point where I'm going to come back to a random walk, back to a Brownian motion, is that you take the loop of this CLE4 that surrounds zero. And it is quite an important question to say, okay, how close this point is to zero and how far away it is from the boundary. So we know that it doesn't hit the boundary. This is something I forgot to tell you. Loops do not hit the boundary and they do not hit each other. And we know that the loop surrounding zero, because of conformal invariance, represents a typical loop because we can just take a loop from another point. And the question is, well, what is the law of these two random variables? So the conformal radius, so the way to measure them, and sadly I will have time to explain if you don't know these terms, but the way to measure them in a conformal invariant way is to measure this as the conformal radius of the domain that is bounded by the loop, and the distance from the loop to the boundary is called the extremal distance. And what was known is that, okay, the minus the log of the conformal radius corresponds to the following random time of a Brownian motion. So you take a Brownian motion, you start on zero, and then you see the first time it exits minus pi pi. And this corresponds exactly to the law of minus the log of the conformal radius. And in fact, this can be done even by a coupling. So in a way that one constructs a minus 2 lambda, one can do a coupling and obtain a random Brownian motion out of the Gaussian free field plus, and one can identify this stopping time with this. However, what is most surprising is that in fact the joint law of the distance to the boundary with the log of the conformal radius can be read in the same Brownian motion, and it is the following. So we already know the log of the minus the log of conformal radius is the first time you exit minus pi pi, and the distance to the boundary, so this extremal distance to the boundary, is will be given by the last time I hit zero before I exit minus pi pi. So it is not a stopping time, it is this weird time. And the way it is proven, and it is not by coupling. So in fact, there is no natural coupling that will associate the two, and we have strong, so I cannot explain why, but there are strong reasons to believe that in fact there is no such a coupling to from a Gaussian from a Brownian motion that comes from the Gaussian free. And just a short idea on how to prove this type of things. So the idea is that if you could grow, if you could imagine that you can grow this set a minus 2 lambda, and in fact this is possible in a way that is continuous. In the district is clear, you are adding one vertex at a time. Here you are growing it continuously. There is a certain normalization under which the harmonic function look from zero behaves like a Brownian motion. And in non-simply connected domains, you can do the same thing. You can grow these sets in a way such that look from the inside, the outside looks like a Brownian bridge in a certain way. And okay, so just to give you an idea. So what happens is that you instead of working on the simply connected domain as we were doing it, you work in a non-simply connected domain, you make a small hole, and then you start constructing these two value sets, but starting just from the outside. And when you start just from the outside, you can obtain the loss you want. You couple them, and okay, just I'm finishing 30 seconds. And what you will obtain is that you obtain either 2 lambda minus 2 lambda, and then you iterate it, and constructing it from the outside to the inside is the same law as constructing from the inside to the outside. So you obtain the first, you just obtain the law of the extremal distance to the outside. And to conclude, what you do is that you need to characterize this joint law, and the way to do it, with this I finish, with the way to do it is to, you work with a Brownian bridge, and you work with a Brownian bridge from 0 to V, which corresponds to put certain boundary conditions on the ball inside. And then you see that what is nice is that the conditional law of this down given the one on the top does not depend on V. And this is exactly the good characterization that we can prove that we do have in this case from where we obtain the result. Gracias. Thank you very much.
Thank you, Avelio. Thank you very much for this really nice talk. Is there any question or comment? Okay, so Avelio, let me ask you a question about your first slides, because this is beautiful, but it's hard to grasp immediately. So when you construct the first random walk from the square.
Yeah, yes, this one?
Yeah, in that picture. So, well, in that picture, you started with a Gaussian random variable, and then you, in each square, you sum an independent Gaussian random variable, but with a different variance, I imagine, or not?
Oh, in this case, so here, what is quite nice. Okay, so in the picture I have here, the green ones have exactly the same law.
Yeah, but not the same law as the red. They have a smaller.
No, so the red one is a harmonic function. Yes, okay. Which represents the extension of the values here. So it is it is not so it's a Gaussian process, phi sub A, but it's a bounded one. So the one which is not bounded is this one. It's a bounded Gaussian process except close to this line. And yes, so it is non-homogeneous. However, the good thing is that it's phi super A, they are homogeneous in a way. And what one needs to do, and okay, and in fact, this phi super A has the same law as this phi super V, because we have exactly the same object. So in a way, we are adding things that have closely the same law, but they are not exactly the same. Okay. This is what it makes difficult for the first result of the maximum of the Gaussian free field to be obtained, because you need to control what is this harmonic function and try to say that in a way it's behaving nicely, but it is not such an easy task to do.
Thank you. Is there any other question? Okay, then let's thank Avelio again. We have